Hi, my name is Michal Moshkovitz. I'm a postdoc at the Qualcomm Institute at the University of California, San Diego, and I'm happy to present the work Unexpected Effects of Online No-Substitution Kmeans Clustering. The main object in this work is clustering, more specifically, center-based clustering. In this kind of clustering, we are given a set of points, and the goal is to find a small set of points that are good representatives of the entire dataset. For example, for this dataset, these 3 points are a good representative of the entire clustering. They define the following partition of the data. Each point is going to its closest center. How do we evaluate how good a clustering is? For that, we use the notion of Kmeans cost. Given a dataset D, the Kmeans cost, of the k-centers C1 till Ck is defined in the following way. For each point, we are looking at the distance to the closest center. Then we sum the square distances. This is the Kmeans cost. A clustering algorithm for the Kmeans cost is the following. Is given as an input a parameter k, which represents the desired number of centers. It's also given n points. The goal is to output k centers. We want to output centers that minimize the Kmeans cost. But the problem is that this problem is hard to solve. So we have to relax the problem. One way to relax the problem is to allow to return a larger number of centers, k prime. And the goal now is to minimize the cost of these new centers. So how do we evaluate what is a good clustering algorithm? Now there are 2 criterions for that. One is that the number of centers that we return should be small. K prime should be small compared to k, and hopefully maybe even k. Another thing that we judge an algorithm by is how close it is to the optimal cost. So what we want is that the algorithm to return a clustering with probability at least 0.9, we want the cost to be at most c times the optimal one, where the number of centers is k. So this is how we judge how good the clustering algorithm is. Solving this problem is known, so it's known how to solve the problem with O of k centers and O of 1 approximation. In this work, we focus on the online setting, on the no-substitution online setting. So here is a motivational story for that. Suppose you're running a clinical trial. You want to test a new drug. People are coming to your clinic, and you decide whether to give them the new drug or not. And then, after you decide, a new patient is coming to your clinic, and then it leaves, and so on, and so on. Your goal at the end is to give this drug to a small set of people. You don't want to give an experimental drug to many people. And second, at the end, you want to make sure that the people that you chose, the patient that you chose to give the drug to, are a good representative of the entire population. So this is exactly the online no-substitution setting. So let's formalize it. We are given points one after another. The algorithm is doing some computation, and then it decides whether to take the current point as a center or not. Notice that the decisions are final, and at the end, we check the quality of the chosen centers. So in the story that we had before, the points are the patients, the centers are the patients that got the drug. At the end, we check whether the people that got the drug are a good representative of the entire population, and in this setting, we check the Kmeans quality. And we want the number of people that get the drug to be small. And in this setting, we want a small number of points to be chosen as centers. So this is the online no-Substitution Kmeans clustering problem. The main question that I ask in this work is, suppose we want a good approximation algorithm, a constant approximation algorithm. How many centers are needed in sufficient? So this is the question that I want to understand. First thing that we have to understand is that new factors come into place when we are talking about the online setting versus the offline setting. So what are the new factors? One is the order of the points. Are the points coming in worst case? Someone is deliberately trying to give you an order that will cause you to take a lot of centers? Or maybe it's average. Points are just arriving in a random order. It makes sense that the order will impact the result. But can we quantify exactly by how much? Another factor that comes into play is whether we know n in advance or no. Do we know how many points will arrive? Is the mere knowledge of knowing n in advance can help the algorithm? By how much? So this is what we want to do in this work. We want to understand how these new factors affect the results. Okay, so here are the main results. First, we separate the analysis depending on whether k, the number of desired centers, is equal to 1 or bigger than 1. Let's start with the case that k is equal to 1. This means that all the points are in one cluster. And the question here is, how can we find at least one good center? So let's separate the analysis into two cases, whether the order is random or whether the order is worst case. Let's start with the case that the order is random. How many centers are needed and sufficient? In order to answer it, here's a known fact. If we have a cluster and we take a random point in it, it's going to be a good center, probably. Given this fact, it's easy to know how many points we need to take a center in the case of k equal 1. We basically can just take the first point as a center. Okay, so we don't need to take a lot of points in centers to get a constant approximation. So let's move on to the case of worst order. Again, we need to separate the analysis, depending whether we know n in advance or we don't know. If we know n in advance, we know that we will have exactly n points. How many points are needed? In this case, what we can do is simply choose a random number between 1 and n, and just take this point as a center. And again, we get a random point, which is a good center. So in this case, where the order is worst case, but we know n in advance, we only need a constant number of centers. What about the case that n is unknown in advance? So in this case is more complicated. The answer turns out to be theta log n. This means that there is a lower bound where we have to take log n centers in order to achieve constant approximation. And there is also an algorithm where log n centers is always enough. The algorithm is simply take the ith point with probability 1 over I. Okay, so we covered the case of k equal 1. And already here, in this simple case where all the points are in one cluster, we already see some interesting effects. We see that knowing n impacts the result, and we exactly quantify by how much. Okay, so now let's move on to the case of k larger than 1. In this case, we separate the analysis depending on the order, whether it's random order or worst order. Let's start with the case that the order is worst case. How many centers are needed and sufficient in this case? Unfortunately, it turns out that in the worst case, there is a lower bound of basically n. The idea is that if points arrive one after another, and each point is very, very far away, it might be the case that each point has to be taken as a center. Otherwise, the approximation will be huge. This is why we need to take all the points as centers. And what about the random order case? So again, we separate the analysis whether we know what n is and whether we don't know what n is. If we don't know what n is, the answer is theta log n. There is an algorithm that takes log n centers, and there is a database where you have to take log n points and centers, and for every dataset, log n points is enough. In the case that we know what n is, the answer turns out to be constant approximation. So just knowing what n is, we suddenly just need to take constant approximation. So what we see here is that we covered the entire online landscape. And so we see this complicated behavior that changes between n points and constant number of points depending on the order and whether we know n in advance or not. And compare it to the offline landscape, which was really simple. So, thank you.